This is Suvarchala working as an associate professor at IARE in the Department of Computer Science and Engineering. In this video, I would like to discuss about single source shortest path problem as well as Dijkstra's algorithm to solve the same problem as a part of design and analysis algorithm lecture series. We have been discussing about greedy technique and its applications from last few lectures. As a part of that, one application I would like to discuss in this video. That is single source shortest path algorithm, and to solve that particular problem, Dijkstra's algorithm implementation, some examples and analysis of the Dijkstra's algorithm. Single source shortest path problem. The problem is here defined as a finding shortest path from source vertex V to all other vertices. Please observe to all other vertices. So from a vertex 1, any given vertex V to each of the other vertices, the shortest path is going to be identifiable by us. That means here there is no single destination. All other vertices are considered as a destination. So the path must be identified from a given source to each and every other vertex considering as its destination. So shortest path we have to find out. Shortest path means it is a minimization problem. That means it's an optimization problem. So this can be solved by using our greedy technique. So let us assume that if you are going to consider 6, from 6 I have to find the shortest path from 6 to 4, 6 to 5, 6 to 4, 6 to 5 and 6 to 1 and 6 to 3 and 6 to 2. So the shortest path must be found from a given source to each and every other vertices as a considering as a destinations. To solve this single source shortest path, a great mathematician, Dijkstra, proposed an algorithm which is named after its invention by him as Dijkstra's algorithm. Strictly speaking, he is one of the founders of computer science, and this is only a small contribution towards his foundings and his findings. Among them, this is one of them only, but many other things are there proposed to and proved by the Dijkstra actually. So this Dijkstra's algorithm, known by his name itself, is an algorithm to find shortest distance from the source to each and every vertex as a destination. Multiple applications are there actually in our day-to-day life routing system. So routing system means from any particular place, the other places we have to find the shortest distance and a routing actually. That is by using maps or a Google Maps can be considered. And another routing system is our communication in networks. So in networks also we have to communicate, and you can consider it as a broadcasting in one application. Broadcasting is a communication from one source to all other nodes, other nodes. It has to be communicated. So in such cases, this type of algorithm is very much useful to us. That means to each destination, it has to be reachable with the shortest time or a shortest distance, etc. So what is Dijkstra's algorithms? This Dijkstra's algorithm is a solution for our single source shortest path problem in a graph theory. And Dijkstra's algorithm works for both directed and undirected graphs. But remember, this algorithm doesn't successfully run on negative edges. That means only the edge weights must be non-negative only. For such edges only, this is considered as a efficient algorithm actually. For if the weights are non-negative, because if the distance anyway it may not be negative, but any other weighted, if you are representing an application as a weighted graph, then the weights may be positive or negative depending upon the application. So, if any such problem has to be solved and which consists of the respective graph consists of negative weights, this algorithm doesn't suitable to such applications. So, for Dijkstra's algorithm, input is a graph G with the edges at E and vertices V, and a source vertex is given from which the shortest path or shortest distance to be calculated to all other vertices, and such that the weights of these edges must be only non-negative actually. What is the output we will get? The output is going to be lengths of the shortest paths or shortest distances from a given source vertex to each other vertex. What is the shortest distance can be identifiable by this algorithm. So how this Dijkstra algorithm works? Approach is given a weighted, connected, directed in general we will use, but it works for undirected also. Graph G, find the shortest path from a source vertex V to each other vertices, and the solution problem is a solution of this problem is the same as the solution for single source shortest path. So that's why the single source shortest path problem can be solved by implementing Dijkstra's algorithms actually. Both are having the same objective, finding the shortest distance from a given source to all other vertices. The problem is also same, and Dijkstra proposed algorithm for finding the same. So this implementation can solve our problem actually. So Dijkstra's approach, how it works actually. It is similar to our Prim's algorithm for constructing the minimum cost spanning tree, which were discussed in previous sessions, but a change is there, modifications are there, approach is different from computing the numerical labels actually. Now, among all vertices not already in tree, it finds the vertex u with the smallest summation value as a dv plus weight of vu, where v is the vertex for which the shortest path has to be as already found on preceding iterations, and dv is the length of the shortest path from source S to V, and WUV is the edge weight from V to U actually. And by using this formula, we can find the smallest to shortest distance, and we'll discuss how this formula can be applicable by using relaxation rule. We'll call it as a relaxation process or relaxation rule. So these are the major steps in our Dijkstra's algorithm. In Dijkstra's algorithm, two sets of vertices are going to be maintained or managed here. V is the set of vertices of the given graph. S is the set of vertices up to or the set of the vertices to which the shortest path from the source has been already determined. That means S is the set of the vertices to which the shortest distance has been already found. So the iteration process has to be continued as long as our V minus S is going to be considered as an empty set. That is, all vertices of V are included in our S. Then we can stop the process actually. So V minus S is the remaining set of vertices. If the remaining set of vertices are pi, means we can stop the process actually. The other data structures needed are two arrays we need actually. D is a array of best estimates of the shortest path from each vertex, or shortest path to each vertex up to that iteration found actually. PA is an array of predecessors for each vertex, through which vertex the shortest path or the path or cost was determined up to that iteration. So the pseudocode consists of majorly three steps. One is, first we have to initialize the array D as well as PI, predecessors as well as the distance calculated from source. Initialization will be done. Initially, the initialization to each vertex will be infinity, and the distance from source to source itself is the 0. And initially the set S is empty. which was not at all the vertex to which the shortest distance one was found is initially it is empty. While there are still vertices in V minus S, as just now I explained to you, that is the vertices to which the shortest distance to be calculated further are available. The following steps have to be repeated. Sort the vertices in V by S according to the current best estimate. So we will estimate at each iteration what is the cost, reachable cost to each vertex. So according to that, whichever the shortest distance is there from, that is, it is going to be sorted order, or we have to select the shortest distance from the source. The vertex has to be selected actually. And the estimated distance, whichever is the estimation distance is the shortest distance is there, or least distance is there till now, that vertex has to be selected as a next vertex actually. So that's why we have to arrange them in a sorted order, or we can select the minimum distance one. That particular vertex is going to be added to our S. That particular vertex is added to our S means the distance up to that particular vertex was computed. So let us assume that that vertex is U, that is the closest vertex in our V minus N S, which is added to S actually. Then we have to use the relaxation rule. Relax all the vertices still in V minus N, which are directly connected to U. What is relaxation? Relaxation means the estimation till now we have done, which are directly connected from U, are the shortest distances, or through this U it may get shortest distance. It has to be selected, or it has to be considered by our relaxation rule. So the relaxation process updates the cost of the all vertices V connected to the vertex which was selected now, if we could improve the best estimate of this shortest path to V by including UV in that particular path. Otherwise, previous path itself is best path, we can keep as it is. How to check the best path? If the shortest distance through U is going to be lesser than the already estimated path, then it can be get updated. Through U, the path is best path actually. So, this is the initialization. We initialized, initially all values are infinity, just now I told, and previous are all nil, and source distance is 0. Source to source is 0, no? So that's why source distance. This is the relaxation procedure. Checks whether the current best estimate of the shortest distance to V can be improved by going through the U which was selected. That means here, let us assume that U, we have some V is there and we have some U is there. UV distance is some X is there. V was already estimated through some other node, or through some other node. The distance V is estimated, let us assume that Y. The estimated distance from source to U is, let us assume that Z. That means from source through U, you can reach V, or through other path which already estimated, we can reach V actually. The reachability distance to V previously estimated was Y, and through, if you are going to consider, up to U is Z, and the distance from U to V is X. So Z plus X is lesser than already estimated the distance at V, that is Y. Then Y can be updated with this value. Y can be updated with this value. That means through U from source, V can be reachable lesser cost comparing with the already existing estimated cost to V, then V can be updatable. Otherwise, V remains as it is. That is the relaxation rule. This is going to be checked all directly connected edges or vertices from U, which was selected as the shortest distance was found already. So this is going to be relaxation small code or code stub. node U, node V, and weight. Now, if distance to V is greater than distance of U plus weight of UV, then distance V is updated with the distance U plus weight of UV. Just now I explained. Then the previous vertex also has to be, that is parent vertex or a predecessor vertex. You can say immediate parent or a predecessor. Vertex to V is U. That means through which the distance is going to be estimated was noted down by us. This is known as initialization, relaxation rule. So that's why the major steps: initialize the graph, source with 0 and other vertices are infinity, and select the shortest path node. Through this node, update the distances which are connected through this node by using relaxation rule. Repeat the relaxation step for all vertices by choosing the least cost node every time. So we'll discuss, or we'll see some examples through which we easily understood the process actually. Now let us assume that this is a small graph was given to us, and let us assume that source is initialized with 0 and all other are initialized with infinity basically, right? So all other vertices are initialized with infinity. But what is the direct connected edges from source? Source is connected directly to B, and source is connected directly with D with a distance 3 and 7 respectively. So from source I can reach B. What is the reachability value of B? B is 3. What is predecessor? A. Through A, B can be reachable, or B cost is going to be 3. So infinity is updated with 3. So just you write B, A comma 3 means A is the parent or a predecessor, and the distance reachable to B is 3 through parent A. Let us assume. See now direct edge. For D again a direct edge is there. That means through parent A I can reach D with a 7 distance. And E is going to be not reachable through any parent. So initially it is infinity. So these are all the remaining vertices. Only the 3 vertices which are included in my shortest path is A only now. From A I found the distances to direct connected edges, having edges directly connected from A to B and D. So that's why those distances are updated with the respective parent. This is the first step. Now what is the distance at B for me? Now 3 by A through predecessor, 7 by A. Now what are the things are available to me? B, C, D, E are available. Among all these vertices, I have to choose the shortest distance or estimated distance vertex must be chosen by us. What are the estimated distances? Are B estimated with 3, C estimated with infinity, D estimated with 7 and E estimated with infinity. Among them 3 is the shortest one. So we will select B is the next vertex. So B is the next vertex means BA3 is the next vertex. B is selected as the next vertex now. B selected means just a color change is there, you observe. B is selected next vertex. Then I suppose to consider from B the direct edges are to be considered. From B the direct edges are here, here and A cannot be considered because already included in my selected vertices. So I have to consider B to C and B to D. Now relaxation rule is applicable. What is the reachability cost to B from source? 3. This is from source, it is 3 reachability cost. What is the cost of B to C? Estimated cost previously it is infinity only. Here infinity, here 7, it is 3. Okay. So B to C estimated cost is infinity previously, but I can reach C. What is the distance? Here reachability cost of B is 3 plus BC value is, that is weight of B comma C. What is the weight of B comma C? It is 4, which is equal to 7. 7 is lesser than the Reachability cost of C is 7 is lesser than the infinity which is already initialized by us. That only we are doing here. That is considered as a relaxation rule. That means the distance of C is greater than, if the distance of C is greater than distance of B plus BC edge weight. Distance of B is 3 we calculated and BC edge weight is 4. 3 plus 4 is 7. Infinity is greater than 7. Then what are we supposed to do? Update our distance of V. So distance of C is equal to combination of these two, update. This is known as the relaxation rule for us actually. So that's why based upon this, C can be reachable with 3 plus 4 and similarly D can also reachable with 3 plus 2 but E remains as it is. Fine. So what is the cost here now? 7, 5, infinity. Among them which is the least one? 5 is the least one. So that means the next vertex to be selected in our shortest path already found can be considered as a D. So D, B5 can be considered. What are the remaining vertices? C and E. From D, what is the cost, reachability cost to C? So from C, I can reachability cost, distance of C is 7, already estimated by us. Now I will estimate if there is an edge from directly D. I have an edge from directly D. C is an edge is there. So that's why I can estimate if the D of C is greater than, distance already estimated greater than the distance of D plus the edge weight comma DC. This is the relaxation. What is D of C estimated already? 7. 7 is greater than, D of D is 5. Distance 5 is plus D distance to C. So DC. So DC is 5. So totally this is 10. Is 7 is greater than 10? No. That means the relaxation rule, previous estimated value is better than the current estimation value. Through D we are reaching now. So that's why we can consider this as remains the previous one. Hope you understand. The relaxation rule need not be updated always if the condition satisfies only previously estimated value to C is 7 and this 7 is better than, through B or through D we are going to consider. Up to D what is the cost? 3 plus 2 is 5, 5 plus 5 is 7, 10. 10 is going to be more than the already estimated cost 7. So it remains as it is. Coming to the E, D to E is 4. So 3 plus, up to D 5 is there and D to E is 4. 5 plus 4 is 9. 9 is greater than the estimated or already existing weight as a infinity. So this is updated but this is not updated. Okay. So this is 7 is there but we calculated as a 10. So 7 is best one comparing with 10. So we can stop that one here. So this is edge updated. Which one is minimum? C is minimum. C is added. According to the C, C to E estimation will be considered. Up to C 7 is there. C to E is 7 plus 6. So 7 plus 6 means here 13. Up to C is 7 and 7, C to E is 13. But what is estimated, previously estimated cost to E? 9. 9 is better one. So we will stop here. So like this we can do by using or considering the edge by edge. If more number of vertices are there, instead of considering this edge, we can arrange them in a tabular column or a table form and which can be easily seen while calculating or solving the numerical problem. Process is same, but while doing this is another example you can try by using the previous methodology actually. Now we will consider the textbook examples which was solved in the textbook as it is and how to solve it, that we will discuss now. Let us assume that this is the graph was given. which is having a distance directed graph, and this is the adjacency matrix representation is there, so that it can be easily accessible by us, the distance between or a weight between any pair of the vertices. Now I'll solve these things here by using how to consider them actually. First, initially, the 5 is the source. If the 5 is the source here, initialization is, the first row is initialization, partially solved, I'll select one by one, and initialization is going to be done by us. What is initialization? Initially, all are infinity except 5 to 5 is 0. Okay, but from 5, so fifth vertex means here, what is the fifth vertex? Boston. So from Boston, we have direct edges to 4 and 6. What is the distance to 4? It is 1500. So 1500, infinity can be updated with 1500. Similarly to 6, it is Newark, it is 250. So infinity can be updated because directly we can reach to Chicago and Newark by covering a distance of 1500 and 250 respectively. Initialization is infinity, so it can be updatable. If 5 is the source, this is the initial values. Direct edges are updated, source to source is 0 and all other are infinity. Similarly, what we have done previously, we can use here as a tabular column like that. Now I'll consider now the next row. What is the minimum among them? This is the minimum. So you observe, for all other vertices, 5 will become only 0 only. So no need to consider by as 5. Okay. Now, among all others, 250 is the minimum. So I have to consider what is the next vertex? 6 must be chosen by us. 6 must be chosen by us. So when we are doing the 6 here, so we have to choose the 250 here. So 250 is minimum. So what is the next one? I have to select 5 here. So next one is going to be 6. The first iteration we are starting. 0th iteration is over. First iteration selected. So the next vertex can be selected is 6th vertex can be selected as a next vertex actually. So the vertex to be selected is 6 now. So what are the vertices are completed now? 5, 6 are completed for me. So 250 is considered as a, so this vertex need not be considered by us further actually. Now what we supposed to do? Which one selected? 6th one selected. From 6 I have to consider what are the direct edges are there. From 6 we are having to 8, you please observe. 8 is there, 1400. From 6 I have 7, 900 is there. Now I have to apply relaxation rule. So what is 8? 8 is existing value is infinity. Right? So what is the value for up to 6? Up to 6 is 250 and 6 to 8 value is 900. So totally it becomes as 1150. Up to 6 is 250. Just we computed now 250 here. So up to 6 is 250 and 6 to 7. Edge value is 900, total 1150. So the reachability cost estimated through 6 is up to 7 is 1150. What is estimated cost of your 7? Estimated cost of 7 is already infinity. Infinity is more than 1150. So we can update this with as a 1150. Second iteration. What is another edge? From each edge we have to consider this relaxation process. Up to 6 our 250 is there and 6 to 8 is 1400. So reachability cost up to 8 is 1650. Reachability cost up to 8 is 1650. What is the estimated reachability cost previous iteration? Infinity. 1650 is lesser value. I can update it actually. And the remaining values as it is. Why? Because from 6 there is no, one more is there. From 6 I have one more edge, direct edge, 4 is there actually. So what is the reachability cost of 4 here? 250 is up to 6 and 6 to 4 is 1000. So we have 1250. Reachability cost of 4 is 1250. What is the reachability cost of 4 previously? 1500. This 1250 is less than 1500. So this can be updated. Okay. And the remaining edges will remains as it is. That is the next iteration. The remaining vertices are having infinity. Only these, using relaxation rule, these are considerable by us actually. Okay, so now let us assume that 250 and 250 is not this row is not considerable by us, already included, and 5 is included, 6 is included. These are not necessarily considerable by us actually, right? So these columns need not be, or these vertices need not be considered. Now what we supposed to do? The next vertex. Which one is the next vertex to be selected? Infinity, 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 1250, 1150, 1650. Among them, 1150 is the minimum one. So if the 1150 is minimum one, to which vertex? 7th vertex. Next selected vertex is 7. So what are the vertices selected by this time? 6, 5, 6 and 7 are completed. Next, what are we supposed to do? From 7, again we have to do the relaxation process. From 7, which are the vertices are there, we have to consider them. From 7, only one vertex is having direct edge, that is 8. What is the reachability cost of 7? Reachability cost of 7 is 1150 plus 7 to 8 is, we are having the value as 1000. So completely to reach 8 through 7, the cost will be 2150. That is the estimated cost of 8 through this 7. But what is the estimated cost of 8? Already 1650 is there. 1650 is lesser than the path which through 7. So that's why this need not be updatable. It remains as it is. Now you observe relaxation rule fails here. 1650 remains as it is. So this is not considered further. Now we have 1650 as it is there, and the remaining things are also as it is, no direct edges, because direct edge is only to 8, but the estimated cost through 7 is more than already existing estimated cost. So it remains as it is. Now we have to select among the minimum. We have only 1250, 1650, 1250 is minimum. Next selected vertex is 4. So what are the set of vertices are completed? 5, 6, 7, 4 are completed actually. So once 5, 6, 7, 4 are completed here, now from 4, I have to consider what are the edges are available. From 4, only one edge is there up to 3. So I have to consider from 4 to 3, what is the estimated cost. The cost up 4 is 1250, cost of 4 is 1250 plus, and 4, 3 edge is having 1200. So total cost is 2450 at 3. At vertex 3, estimated cost is 2450. What is estimated cost previously? Infinity. But infinity is greater than 2450. So this can be updatable. The remaining things as it is actually. So 4 was selected. So from here we no need to consider further 4. Now we have to consider 2450 is there, and the remaining things happens directly as it is 1650. So next one is 1650 remains as it is here. 2450 is updated. Now which one is least one now? Again here in this case 8 is least one. Next selected vertex is 8. So we can have 5, 6, 7, 4, 8. From 8, what are the edges are directly connected? We have to consider for further relaxation. So from 8 it was connected only one vertex, that is 8 to 1. Estimated cost of 1 is here. We are going to have cost estimated up to 8 is 1650 plus 1700 is there. So totally 3350 at 1. So at 1, 3350 is estimated, which is lesser than infinity. Okay, from 8. And the remaining as it is remains, and we selected 2450 and 1650 was already selected. Now among all these available values, we have to select next 3. So what the set included is 7483, and from 3 what are the edges are connected? Edge 2 is connected, vertex 2 is connected, vertex 1 is also connected. So what is vertex 2? So 3 estimated cost is, the estimated cost of 3 is 2450 plus 31 edge. So what is 31 edge? 31 edge is having 1000, so which is equal to 3450 at 1. So 3450 is greater than 3350, so this need not be considered by us. So 3350 remains as it is. We will consider for 2. For 2 also 2450 up to 3. So the cost of up to 3 is 2450 plus 32 is 800, which is equal to 3250. Already estimated cost is infinity, so we can consider it as a 3250. Among them, the next selected vertex is 2, and the included are 5, 6, 7, 4, 8 and 3 and 2. So we can have the respective process. Okay, now we are going to consider here the respective process is going to be continued till we are going to estimate or include all vertices. 2 was included, then the remaining 1 was included. So this way we can consider whatever the processing or the vertices are going to be selected by using our relaxation rule. So once the relaxation rule is there, we have to consider the respective process is going to be eliminated by us actually. So this was a solved example which was solved here in this screen, which was taken from the textbook as it is. The calculation was explained to us. This is the way we can calculate. Now by end of the last iteration, whatever the values are there, these are all shortest distance from the source 5. 5 to 1 is 3350, 5 to 2 is 3250, 5 to 3 is 2450 and so on and so forth. And at each process, the order was given, no? So in that particular order, we can consider the path. So 5 to 1. 5 to 1 means we have to pass through it. 5, 6, 7, 4, 8, 3, 2. So 5, 6, 7, okay. And from 5, 6, we have to consider the respective paths have to be calculated by us. Then the relaxation can be done. If you want path also, whenever we are updating, the predecessor also has to be noted down by PI, must be noted down by us, so that it can be useful to us actually. Dijkstra algorithm correctness can be proved by using induction method on number of vertices, and the main disadvantages of Dijkstra's algorithm is it cannot work for the graphs which are having negative weights. But Floyd algorithm was proposed Floyd proposed an algorithm which allows or works on negative weights also. But there is also one restriction: there should not be any negative cycle. Formation of negative cycle should be avoidable by us. Can you find any counter example for Dijkstra algorithm or not based upon this negative weight? We can take an example and you can check it once. And this Dijkstra's algorithm is applicable for both directed and undirected graph. And efficiency, we'll discuss these two characteristics after algorithm explanation. But remember, Dijkstra's algorithm should not consider as a same as a Prim's algorithm. Please remember, because Prim's algorithm is for construction of the minimum cost spanning tree. That means we are construction of spanning tree by adding edges. But Dijkstra's algorithm, here there is a difference actually. Why? Because here Dijkstra's algorithm, we are finding the shortest distance from source to each other vertex we are finding here. Right? Maybe logically we are taking some steps same, but it can be considered as a different one. And one more example, a sequence of operations can be considered by using here sequence diagram illustrate the operations of Dijkstra's algorithm. You just observe in the first algorithm initial graph, all nodes are having cost as infinity. You observe all other vertices are having the cost is represented inside the block, and you observe, and vertex names are outside the square represented. So S is the source, 0 distance, all other distances are made as a infinity initialization. Second one, direct edges are from source to, we are having source to U is there and source to X is there. So 10 and 5. So you observe the red mark edges are there. So we have to update the respective vertices if the distance, already estimated distances are greater than the current distance. Yes, the estimated distances are infinity to U. So that's why it was updated with the 10, and to X also it was previously infinity, and now we can reach from source with 5 direct edges there, it was updated. The next one, which one I have to select, because D is over already, source S is over, U, V, X, Y are there. Among them, the shortest reachable distance estimated value is 5. So I can select next X. So the rectangle made it as a darkened one, which are selected, those are made it as a darkened. 5 was selected. From 5, I have to consider all direct edges. So I have a direct edge to U, I have a direct edge Y, I have a direct edge to here Y also. So 3 edges I have to consider. So direct edge to U is having as a 3, but 3 plus 5 is 8. It is also 8. No need to update. 8 remains as it is 8. No. And here V is reachable 14, because the distance of the cast 5 is, X is 5. 5 plus the edge weight from X to Y is 9. 5 plus 9 is 14. Previously it is infinity. 14 is lesser one, updated 14. And we'll see for Y also. Y is previously infinity. The cost of X is 5, and the distance or edge distance is from X to Y is 2. 5 plus 2 is 7. So Y is updated with 7. That means the comments are written here. Choose the closest node to S as we initialized D of S to 0, and it is S actually. Coming to the next step, fourth one, what are the remaining vertices? We are having U, V, Y. So because already S is over and X is also over, S reachable distance is 0, X reachable distance is 5. Among the remaining things, 7 is the least one. That is, we have to include the completed value as the shortest distance as Y. From Y, I need to check the values remaining vertices, that is Y to V and Y to U. So Y to V is the distance cost we are having is 4, and up to Y is 7. 7 plus 4 is 13. Already the value is 14 at V. It is updated. Why? Because 14 needs go more than 13. So through Y you can traverse, so that the reachability distance is 13. Similarly, Y to U there is no any edge. So it remains as it is. So 3 vertices are over. The remaining vertices are U and V. Among them, U is reachability cost is 8 less. That will be selected next. U to V, the cost is 1. The cost of U is 8. 8 plus 1 is 9. Previous distance is 13. So 9 is better one. So 9 was updated. So the last one is 9 only. Now you please observe here the distance, shortest distance from S to S is 0, S to U is 8, S to X is 5, and Y is 7, and V is 9. by having the predecessors. Whenever we are updating, we will update the respective predecessor also. So that's why the predecessors provides us path to the respective nodes also. So this is an algorithm. Algorithm is provided by using either priority queues, or you can consider, or by using array representation. We have to take always a minimum value. Minimum value can be chosen by using a queue with the order of n, or by using a heap. So min heap is going to be generated as we discussed earlier also. Minimum can be found from array elements with a complexity of big O of n, normal minimum algorithm, or minimum can be found by using a heap concept. So finding a min heap and the topmost can be removed with a log n complexity. And moreover, the graph can be represented either using adjacency list, or we can represent by using adjacency matrix also. For example, when we are considering this minimum and the list is going to be maintained, this is the way we can consider neighbor distance, etc. And the pseudocode can be considered by using relaxing the edges, etc. So this is the normal algorithmic notation. Pseudocode we can consider the Dijkstra's algorithm of initialization, which we have been discussing throughout our session, how the initialization has done, and Q and S, two sets of vertices we are considering. Now you observe here extract min. This extract min, depending upon this extract min only, the complexity change will be considerable. The min extraction can be done if the queue is maintained as a priority queue, or if the queue is maintained as a heap actually. Based upon that, there will be a small change, there will be a change in our complexity of the algorithm. So the simplest implementation of the Dijkstra's algorithm stores vertices in an ordinary linked list, that is adjacency list or an array. Okay, so the lists are good for the dense graphs. Dense graph means more vertices are there, completely connected graphs, etc. And array is more useful for the sparse graph, less number of edges. It is lesser than mod v square. You can consider it as a array representation. Let us assume that according to our algorithm, you observe here the loops you are observing. This is order of v will be there, and here we are having one outer loop is there. Here we are having inner loop is there actually. So depending upon the number of edges to be get relaxed, and extract min is inner loop is there. So depending upon these two, here one loop is there here. It may be either log n or log v, or it may be log edge. Yes, based upon the edge weight, no. So log e edge weight will be there, or if it is a big O of e also, depending upon the way we are extracting the minimum actually. So you observe these are the inner loop, two inner loops are there. Based upon the inner loop complexity, the total complexity is considerable. So if we are representing list, while loop is going to be order of v, outer while loop, and find and remove the minimum distance of vertices with the order of v we are considering. If it is a list, no. So normal we are considering. Potentially e updates. So maximum number of edges updations will be number of edges, total number of edges. So the update cost is 0, 1. Big O of 1, constant cost. So the total update cost will become as a e mod e can be considered as update cost. So the total time is big O of mod v square plus mod v, which is big O of v square. So you observe when we are considering this as a outer loop is also v, inner loop is also v, no. So that's why we are having, if the representation is in the form of the list and the minimum is found or calculated by using normal min function, which is order of v only. So that's why the time complexity of Dijkstra's algorithm, if the minimum cost is based upon the normal list structure, then we can complexity is quadratic complexity. Let us assume that you can use priority queues, that is array representation can be considered. Then sparse graphs are there. This is best suitable here. Sparse graph means number of edges are less. That means number of edges are lesser than the v square edges, mod v square. That is, it's not completely connected graph. Then initialization is going to be considered, and we will, to find our minimum value, we will build a heap. So the heap building as well as removing all will take only log mod v will be considered here. So that's why the potentially mod e updates are there as usual. So the update cost is going to be here. A decrease key will be considered using a decrease key. That is, minimum is there, no heap we are updating, no. So log mod v will be there. The total time complexity is big O of mod v into log v plus log e. So that's why we will consider it as a mod v log v plus mod e log v. So this is approximately equivalent to, because mod e is lesser we are considering, no, so that's why mod e log v can be considered as the total time complexity. Mod e is log big O of mod e, assuming the connected graph also, as we discussed earlier actually, because e is equal to v square, so log e is equal to 2 log v, so that's why log e can be considered as a log v also. Now based upon this, the time complexity can be either big O of n square or big O of order of e log n can be considered, or in other words, n is the number of vertices, big O of v square or big O of e log v can be considered based upon the representation, based upon the minimum value is going to be computed by us. Thank you for watching this video, and we will come with some other topic next video.
Like, share and subscribe. Hit the bell icon for more updates.